Okay, welcome everybody. Today we have an MSc seminar by Mikhail Novitsky. Mikhail finished his BSc degree in computer engineering at the Technion in 2019. And he has been pursuing his MSc degree since 2021 here at the Technion Autonomous Systems Program, TASP. All right, Mikhail, go ahead, please.
Okay, so hello everyone. Today I will present the work that I did under the supervision of Associate Professor Vadim Indelman, which discusses how we can use previous knowledge in an online non-parametric belief-based planning. So regarding the outline of the presentation, we'll start with some introduction and motivation. We then will briefly go over the related work. Then in the approach section, it is broken down to two main points. The first one is experience-based value function estimation without planning. And the second one is our algorithm IRPFT, which incorporates the first approach in an online planning algorithm. We then will move to the evaluation section and conclusions. So autonomous agents are everywhere around us. We have self-driving cars, fruit-picking robots. We have agents that can play StarCraft, agents that trade stocks, and all of them have two basic components. The first component is perception, which is the environment representation and understanding, and it usually deals with the uncertainty. The uncertainty stems from many different reasons. We have noisy measurements where sensors have an inherent noise in them. In many cases, we have only partial information about the world, so we don't know the true state. And we possibly have multiple input sources that can also be conflicting. The second component, which we also discuss in our work, is decision-making, which involves planning into the future and taking actions. It needs to handle uncertainty and dynamic environments. In many cases, safety constraints are also important, and it has to have a mechanism to predict the future. And usually decision-making starts from scratch at each planning session while discarding previous information. But previous planning session might have a valuable data that we already have, and we can somehow use it. And reusing previous information can be also efficient and time-saving. Partially observable Markov decision process, or POMDPs for short, is a mathematical framework for modeling decision-making problems under uncertainty, where each problem is characterized by a 7-tuple. S is the state space, A is the action space, O is the observation space, PT is the state transition model, which is a Markovian given current state and action. PZ is the observation density function, which is Markovian given current state. State reward function, which is a function over Sk A and Sk plus 1, and current belief, where the term belief means probability distribution over states. So basically, POMDPs is split to two main approaches. The first one is a parametric approach, where beliefs are assumed to have a certain parametric form. And the second one, which we also use in our work, is a non-parametric approach, where beliefs are approximated using samples. It includes statistical techniques that are used to estimate probability distribution from samples and propagating this probability, such as particle filters. We don't have any parametric assumptions regarding the functional form of a distribution. And each belief, as we said, is approximated with a finite number of state samples. A typical reward function of a belief node in a POMDP is formulated as expected reward over states, but it is not always enough. Because we want to have a reward that is a function of the current and the next beliefs. What it allows us is quantifying uncertainty using information theoretic measures such as information gain and differential entropy, is needed explicitly in information gathering, active sensing, and other tasks. And typically, it's more computationally demanding than the expected state reward. So the expected state reward is just calculating a weighted average, which is O of n given n samples. And differential entropy, for example, using Bohr's approximation, is O of n squared. Every point DP problem can be cast to a MDP problem, where the B is the space of all possible beliefs over states. Note that the space here is each state in the space is a distribution. A has the same definition as in point DP. Tau of BK plus 1 given BK and AK is a belief transition function that we know how to calculate. And the reward and the initial belief are same in the point as in the point DP definition. Several terms that we will use throughout our work. So policy pi is a mapping from belief space B to action space A. GK is the discounted return for starting at belief BK and with horizon L. V pi of B, which is the value function, is the expectation over the return given that we follow policy pi and start from belief B. Q pi of B and A is an action value function, which is the expected return following policy pi when we start from belief B and take action A. So here we have a general autonomy loop, which is relevant to all of the agents there are. So we have some current belief, then we plan on the uncertainty and find the optimal action or action sequence of policy, perform this action, get measurements, update the belief, and the loop goes on until the mission is complete. We mark by HK the history, which starts with the belief B0 and the actions and observations up to time K. And the belief, by definition, is the distribution of the states given the current history. So regarding the computational complexity of point DPs, finding exact solutions is very hard. We have the curse of dimensionality, which means that for any additional dimension of the state space, we need to have exponentially more samples to approximate the value function. Have the curse of history, which means that the branching factor, which is dictated by the size of the action space and observation space, is huge for almost every real-world problem. And on top of that, all of the spaces, the state, observation, and action spaces might be continuous, adding to the computational complexity. Online algorithms are trying to find an approximate solution given given constraints. So basically, they all work in the same manner. They sample the belief space and build a partial belief tree or graph. They operate within limited budget constraints such as time or number of iterations. They possess the anytime property, which means that as the algorithm runs more, it produces better and better estimations. And finally, they find the optimal action or policy giving according to the sample tree. So here we have an example of an despot alpha algorithm by Gard, which is an online algorithm. And we have here a tree that was partially sampled. And each one of the nodes is approximated with a finite number of particles, as in our work. One of the most famous algorithms for online search is MCTS, or Monte Carlo tree search. And every one of the iterations consists of these 4 consecutive steps. We have the selection step, which means that we apply some selection policy that traverses the tree until we reach an expandable node. We then make an expansion to expand the tree, to expand this node 1 level deeper. We perform simulation, which is an application of a default or predefined policy up to some horizon L. And then we backpropagate the values and update statistics up until we reach the root. So in terms of related work, we have online solvers that deal with the state space expected state reward. So we have PoMCP by Silver et al., which was one of the first algorithms that applied Monte Carlo research to PoMDPs. We have Despot Alpha by Somani et al., which also used an online algorithm, but it wasn't MCTS, it was a heuristic search. And PoMCPOW by Sandberg et al., which also deals with expected state reward and continuous action observation spaces. Regarding online solvers with belief-dependent rewards, as in our work, so we have the PFT-DPW by Sandberg et al., which is the main algorithm that we also are based on in our work. It uses a constant set of particles in each belief node in the tree and approximates reward over the belief. It deals also with continuous state action and observation spaces by using progressive withering. We then have IPFT by Fisher et al., which is based on the PFT-DPW algorithm, where they propagate each time a small number of particles throughout the tree, and then average reward calculations of nodes without keeping the particles explicitly. And the raw PoMCP, where they propagate a small set of particles each time, and they add them to the nodes along the way in the tree, where each belief node has a better approximation as the algorithm continues to run. And the calculation reuse, we have one work by Farhi and Dindelman, which is called BSP, where they assume the sparse sampling algorithm for calculation reuse. So here we have a summary of the algorithms and the difficulty of the problems with which they cope. So we can see the first algorithms assume discrete action and the observation spaces. The reward is over state. And also when we are talking about the discrete action observation space, so the reuse is trivial because we can just take the sub-branch of the experience that we produced during the planning session. We have PoMCPOW and PFT-DPW, etc., where they deal with continuous spaces. And the IXBSP, which assumes sparse sampling algorithms, so the state action space, the action space must be discrete, and they also apply reuse. And in our algorithm, all the spaces are continuous. The reward is over the belief, and we apply reuse. So when we started our work, our motivation was the following. Solving PoMDPs with continuous state action observation spaces is hard, as we mentioned. And the probability to sample same belief twice is 0. And each planning session starts only with root node and previous information is discarded. But we had a feeling that previously sampled beliefs can still provide useful information during current planning session. And what we do in this work is to use previous trajectories to get efficient estimation of the action value function given some policy pi. So our two main contributions are theoretical justifications for information reuse in a non-parametric setting, first without planning, and then we apply our approach and produce a novel MCTS-based algorithm that incorporates information reuse in an online planning. So let's start with the first section. So here we assume that we have an access to a dataset D that contains trajectories with returns of an expert agent that followed some policy pi. And we have current belief BK and action AK. So here we can see it mathematically. D consists of those pairs of tau I and GI. And now the tau I is a trajectory with horizon D. And we have double indexing because we can have beliefs that we can have trajectories that start from the same beliefs. So actually, it is a forest that consists of trees. And here we can see it visually. So given current belief BK and the action AK, we have those previous trajectories, and we want to somehow estimate the action value function. But the question is, how can we do it? Because as we mentioned, we deal with continuous state action observation spaces. So the probability that we have trajectory that starts with BK and AK is equal to 0. So we do the following trick. Here we have an illustration. So we draw this link from BK using AK to the first propagated belief in the trajectory. And we use the trajectory reminder, which is termed here by tau I suffix. And of course, we know that we cannot just do this. We need to make some corrections. So mathematically, given trajectory tau I, which starts with belief BKI and AKI and tau I suffix, we draw this link from current belief and action using current action to tau I suffix. And actually, we have to make 2 adjustments after making this trick. The first one is that we need to fix the return. So remember that the discounted return is a sum of future returns multiplied by gamma. And when we change the initial belief and action, so we need to subtract the previous first reward and add the current reward. And the second one is that we want to adjust the likelihood of this return, because the probability of the trajectory suffix changes, because now if previously it was sampled from BKI and AKI, and now it is sampled from a BK and AK and the policy line. So visually, we need to fix this the reward of this link, and then account for the distribution of the trajectory tau I suffix. So let's do a quick recap of the important sampling. So given some target distribution P of X and proposal distribution Q of X, we can estimate expected value under distribution P of function of X. Given samples from Q, if we multiply each sample by the likelihood ratio of the distributions, where Q must satisfy that the support of P is contained in the support of Q. And in our case, we can apply it directly if we have NIS partial trajectories, and the proposal distribution is given by BK, AKI, and pi, and target distribution is given by BK, AKI, and pi. We can define an important sampling estimator with the likelihood ratio of the trajectories. And we notice that actually we have many different distributions, because each initial belief and action dictate a different distribution. So what we want to do is to use multiple important sampling estimate. So in order to do that, we designated by M the count of unique distribution, where each one is each distribution is comes for a different belief and action, BKM, AKM, and the sample count of from each distribution is marked as NM. So using this double indexing, the dataset D can be reformulated, where M is the index that goes over the distributions, and L is the index that goes over the samples for each distribution. Quick recap of multiple important sampling. So we have M proposal distributions. NM is the number of samples from each distribution. XIM is the I sample from distribution QM. And WM is a weighting function that must satisfy the following property. So we can just plug in the proposal distribution and target distribution and get the following estimator for the action value function. And here we have the likelihood ratio of the trajectories. So visually, we can see this dataset that contains 3 trajectories and belief and action BK and AK. And we somehow combine these trajectories to get an estimation of BK and AK without planning. So the question is, how can we calculate a single term of the trajectory likelihood of tau I suffix? So we can just use the Markov assumptions and chain rule, and We have the full derivation in the paper, but it turns out that the term is equal to the following for products. And what we can see that it might be not it might be pretty expensive to estimate this term, but luckily we don't have to make the full calculation. So here we show our first lemma, so that the likelihood ratio of the trajectories is actually equal to the likelihood ratio of the first propagated beliefs. And the proof is the following. We plug in the term for tau I suffix, and we use the chain rule. We separate the remainder of the trajectory, and it cancels out because it's common in both of them. And we have the likelihood ratio of the propagated beliefs. So now we can, this estimator takes the following form where we have the likelihood ratio of propagated beliefs. And this term is much easier to calculate, and we show the exact calculation in our paper. So far, we've seen that the given belief K, action AK, and dataset D, we can estimate the action value function without planning. Now we will move on to the next section where we show our algorithm and how it incorporates this approach in the MCTS plane. We name our algorithm incremental reuse particle filter tree, or IRPFT for short. It's based on the PFT algorithm by Sandberg et al. And it incorporates trajectories from previous planning sessions for fast estimation of Q of BK and AK. So here we have, when we reuse previous trajectories, we have two main issues. The first one is that the horizon of previous trajectories is shorter than the current horizon. So it means that, for example, previous trajectories might have looked 10 steps ahead, and the current trajectory looks 11 steps ahead. And the second one is that the previous trajectories were sampled from different distributions, where in order to handle this, we apply our approach. So in order to fix the horizon problem, we make a horizon alignment, which means that we have here some propagated belief D with horizon D, and we want to extend its horizon by delta D. So it is done by making a post-order traversal over the tree and updating the values. And we have the full algorithm in our paper. And after we finish with this procedure, we can reuse trajectories from this subtree because each one of them looks exactly at the horizon that we currently are interested in. The second lemma deals with how much it costs us to do this horizon alignment. So given an MCTS tree T with horizon D, number of simulations M and then nodes, extending its horizon by delta D will require adding at most M multiplied by delta D nodes. So the proof is pretty straightforward. After M simulations, the MCTS tree contains at most M leaves, and each leaf is extended by delta D. So now, given that we already filled the horizon for previous reused trajectories, we need to account for different distributions. And we use the same estimator that we developed in the first part. But we note here that we don't have the pi superscript. The reason is that the tree policy varies between different simulations. So the trajectory distribution is non-stationary, which makes this estimator a heuristic estimation of the Q value in MCTS. Its proof is yet to be established, and we plan to address it in the following work. And we also notice that regular calculation of this estimator will take the complexity of O of M squared multiplied by N average. And because we do it incrementally, we want to somehow make this update more less time consuming. So the third lemma talks about how we can incrementally update the multiple important sampling estimator. So it turns out that instead of M squared multiplied by an average, we can efficiently update it incrementally, given L samples from identical distribution M tag, with the following runtime and space complexity. So here we have a quick proof. The full derivation is in the paper, so we can look at the inner sum. And in case m is not equal to m tag, which means the distribution is not equal to the one for which those new L samples were sampled, we just need to update to make the following update to the denominator, which is O of 1. And this is made for all samples in all distributions. So this is the time and the space complexity. In case it is the same distribution, so we have to update the denominator for existing samples. And for the L new samples, we need to calculate this term from scratch, which takes the following time and space complexity. Another issue is how can we determine which reuse candidate B minus we want to reuse for belief B and action A. So remember that we have many such candidates and we need to somehow choose among them. So we have two main considerations. The first one is that we want to reuse propagated beliefs that have a large visitation count, which is pretty straightforward why we want to do this, because then the speed up that we will get will be larger. And the second one is that we want to reuse propagated beliefs that minimize the following term. And I explain it briefly. So we have a function here, fd of b minus b and a, which measures how close is b minus to propagated belief sampled from the correct distribution given by b and a. And we know that this calculation is computed across the entire dataset, so that it needs to be cheap for evaluation. And an example for such f of d is expected value difference, a norm of the expected value difference between b minus and the most likelihood estimation of the propagated belief. And we also know that even if the probability of the reused belief is low, so the estimate will still be consistent because it will have low weights. The second issue is how we can decide how many trajectories we reuse and how many trajectories we open from scratch. So on the one hand, we want to reuse trajectories because then we get a speed up in the calculation. On the other hand, the previous trajectories might be less relevant to current belief B and action A. So we still want to generate new trajectories. And in our work as a compromise, we aim to have the same ratio of reused and non-reused propagated beliefs. So now we will go over all of the steps of the algorithm, and due to space limitations, we didn't include the full algorithm here. It is included in our paper, and we'll just go over the summary of the different steps that we discussed. So in case reuse is possible for B and A, we calculate B minus following this minimization problem. We then fill its horizon to match the current horizon that we are interested in. We update the counters of MCTS using the counter of B minus. We then estimate Q using the incremental multiple importance sampling update as we showed. And we add B minus to the children of B and A. Great. So we reach the evaluation section, and here we assess the IRPFT by comparing it to the base version, which is the PFT algorithm by Sandberg et al. And our evaluation focuses on two main aspects. We have a runtime, and then we have the accumulated reward, or the actual return that the agent received during the simulations. And we measure statistics for each one of them. And we do it for a different number of particles. Our problem domain is a standard LiDAR 2D problem with continuous action state and observation spaces. And in this problem, we have beacons along the way, which minimize uncertainty when passing near them. And we have a goal that we want to reach. So we have sort of a trade-off when we want to move from the start point to the goal. The full parameters are in the paper, but we will talk briefly about few of them. So we use the horizon of length 20. We did 1,000 iterations per planning session. The reward is assumed to be a linear combination of expected state reward and the differential entropy. And for each particle number, we used 100 random scenarios to generate a better estimation of the actual return and the runtime. So here we have the results for the runtime, where the PFT algorithm is in blue and our algorithm is in red. So we can see that it is pretty consistent that our algorithm performed better as in all particle numbers. And actually, the graph that is more interesting is the speedup graph, which shows how the speedup factor that we got from using our algorithm. And we can notice that we have here a sort of a saturation at 1.55. And the reason is that the reward calculation has a quadratic complexity in the number of samples. So pretty fast, this becomes the dominant calculation in the tree. So the speed up just depends on the amount of reward computations that we save compared to the reward computations that we need to do from scratch. Here we have the graph of the accumulated reward of the actual return that the agent received. So we can see that we got pretty much the same results. So we got here speed up without compromising on the accumulated reward. So in this work, first we show the theoretical justification for action value function estimation from data without planning. We then integrated this approach in a novel MCTS-based algorithm, IRPFT, and showed how we can implement it. We then did an empirical study that shows that we actually got a runtime performance without compromising on the accumulated reward. And we have several future research directions, such as the consistency of the estimator in case of MCTS and some more. And that's it. Any questions?
Thank you, Michael. All right, we have time for questions for the audience. Any questions? Going once, going twice. No questions. All right. So great job, and thank you all. And
thank you.
See you guys next time. Thank you, Michael. Bye for
Thank
now.
you. Bye.
Thank you.